Welcome to a KNAUER HPLC Columns tutorial with the topic Polymer Gel-based stationary phases. So if you already listened to some of our tutorials about columns and stationary phases, you know that there are different base materials, silica gel and polymer gel. And in this presentation, we want to talk about KNAUER's columns that are based on polymer gels. Typically, these columns can be divided into ion exclusion columns, GPC and SEC columns, and ion chromatography columns. But in the KNAUER world, nearly all polymer gel-based stationary phases that are sold belong in the group of these ion exclusion columns. And what they are for, how they can be used, and how they are built up, this is what we want to talk about here in this presentation. So first, let's have a look, what is this ion exclusion mode? First of all, it's something we just call ion exclusion mode, but in real, it's much more difficult. But to give you, we have to give them a wording how it is called, this mode. So we talk here about ion exclusion chromatography. Here, the stationary phase consists of a resin, so a polymer gel, and brought on this polymer gel are little charged groups that can differ. The mobile phase always consists of water and maybe a little bit of acid, sometimes a really low organic content, but typically you use only water and maybe an acid as a modifier. And the analytes that are used here are mainly sugars or other carbohydrates. Another name, how to name these columns, could be sugar columns. So sometimes on the market they are called columns for sugars or sugar columns. And this is caused by the analytes. But they are not only for sugars. Some of the modifications can also be used for organic acids and alcohols. And from the analyze here, you see that this is a really typical stationary phases for the food industry. So sugars, organic acids, alcohols, you can analyze a lot of soft drinks or wine or beer with it, to get an idea of the content of sugars, organic acid, and alcohol here. So as I told you before, these columns are called ion exclusion columns just to give them a name, but really it's a combination of a lot of separation mechanisms happening in these columns. It's really complex, but to sum it up, you have the main mechanisms, ion exclusion and ligand exchange. But also happening here are always some kind of ion exchange modes. A little bit of size exclusion is always occurring, and there are also different partition mechanisms for every analyte happening in this column. So this is the reason why it is really hard to say for which analytes, which column might be the best one useful. So we always offer a screening for these columns. So whenever somebody is interested in analytes on these columns that we did never analyze before, we would always recommend to have a test chromatogram in the KNAUER lab, because you can't, with any example application, you can't imagine if the separation might work, because it is so complex to see these mechanisms. So the both mainly occurring are ion exclusion and ligand exchange, and this is why I want to explain shortly what happens here inside the column. So we're talking about ion exclusion when you have something like charged groups on your packing material. So this is a schematic drawing of packing material with pores here. So also in a polymer gel, it is the same as in a silica gel. You have a packing material that is porous. And in the pores and on the surface are these little charged groups here. In this example, it's a negative charged group. So neutral molecules can go inside, outside the pores. So there's no problem. If you have a weakly charged negative molecule, like a weak acid, it will have some difficulties to get inside here because it gets a weak repulsion. And the stronger the acid gets, the harder it gets. So if it's really a strong acid, it can't go inside any pore. So you have an ion exclusion. So this one here is excluded from the pores and will elute very, very fast because it can't penetrate pores and go out. And the way through the column for this molecule will be very much shorter than for this one or this one. So maybe you are familiar with size exclusion. It's nearly the same mechanism. There, a molecule is just too large to go inside the pores. And for ion exclusion, the molecule is too highly charged to go inside the pores because it is, this strong repulsion is happening here. The other mechanism is the ligand exchange. So as we saw before, typically saccharides can be analyzed on these columns. And you have often inside the column your polymer gel, and it is modified with a metal ion. So maybe it's positively charged. And you have here a negatively charged saccharide group. And they are going to have an exchange here. It's a really complex mechanism, but this is the basis of what's happening here, an interaction of polar groups from carbohydrates with metal ions on the polymer gel. Yeah, typical methods for these columns are really, really easy. So whenever you find a column that's working well for you from these polymeric ones, it will be a really easy method that you can use. They are always isocratic. They are most often organic solvent free, so you just use water as an eluent, but you have to use really high temperatures. So typically we start at 60 degrees Celsius, but normally it's more 70 or even 80 degree. This is caused by the polymer gel. It is really, it is not stable at high pressures. So you can imagine a polymer gel is something really soft. If you fill it inside your column, you have a completely filled column. And if you now get a lot of pressure on it, you will compress your polymer gel because it is so soft. And even if you take the pressure off, it won't get back to the normal state anymore. So when you use these columns, you have to start at really low flow rates and start to rise the temperature. And after a while, you can also rise your flow rate softly, just not to extend the pressure range of the column. At the same time, you use most often refractive index detection. This is caused by the molecules, so sugars, organic acids, alcohols, other carbohydrates can most often not be seen in a UV detector. And here you use the refractive index. And this very nicely corresponds to the isocratic methods because the columns don't use anything else. They can be run with isocratic methods, it's no problem. And the RI detection can't be used with a gradient. So this is a perfect match. So overall, methods are really easy, really robust, cost-effective because you just use water as a mobile phase, and they are really eco-friendly for the same reason. KNAUER's column family for these kind of analysis is Eurokat. They are running, as I told you, at slow methods, at classical HPLC. It's nothing for UHPLC, and you need a high temperature. So the type here, the polymer gel itself, it's a sulfonated cross-linked styrene divinylbenzene copolymer. And the cross-linkage that defines kind of the pores of the material is about 8% for one form, the H form, and all other forms have 6% cross-linkage. So these have a little bit larger pores than this one, and you can get it in different particle sizes. So here now a little bit more about the 5 ionic forms. So the Eurokat H, this is the most versatile one. So whenever you want to analyze mixtures of organic acids, sugars, alcohols, you will use the Eurokat H form. Whenever you have carbohydrates up to a polymerization grade up to 4, column PB and CA would be perfect, and going to greater oligomers up to DP8, we have the sodium and the silver version. So I hope I gave you a good idea of these columns. So whenever you have an application and you can imagine that this might work, one of these columns might work, you are always highly welcome to contact us, because we would like to scroll our database if we already analyzed something like your analytes. And if not, I recommend to have screening for the best column, because this is the only way to foresee which column would be the best for you.